So the next talk is from Chorowski. I will keep the introduction short. Professor Chorowski, I believe all of you have heard his name. He's a pioneer of attention-based end-to-end ASR, and he has much influential research about unsupervised speech representation. Okay, Yang, the stage is yours.
Thank you for the invitation. Thank you for the introduction. And I guess it's excellent timing that I'm speaking after Herman, because indeed the two talks are pretty related. And I've entitled mine from sampling rate to content rate, because this is in a nutshell something I've been trying to achieve for the past few years. So let me explain the idea to you. So when we do representation learning, we take the raw waveforms, and then we apply some algorithm, an autoencoder or CPC or wave-to-vec, right? And we are getting these content vectors, and then we apply a simple model for a downstream task, such as phoneme recognition or something along that line. And there is a tacit assumption that the optimal rate for the vectors is basically a multiply over the sampling rate, right? So we set our microphone in a certain way, and then this basically determines all the next steps that the system will be doing, even though the contents that come here perhaps are at a different rate. So to put it differently, right, we start with this waveform, and then we decide to extract the latent features every 10 milliseconds or every 20 milliseconds, because that's easy. But then this basically doesn't coincide, right? This doesn't collocate with where the sounds are, where the segments that we wish to detect are, which ties us also to this segmentation and clustering approaches of Herman. So what we would want instead to do is to align the representation after the representation learner to the actual content. So the content rate, not sampling rate, which can be achieved by detecting phoneme boundaries or by learning oversampled piecewise constant representations, which is slightly easier to do in a neural setup, because we can defer the decision on where are my symbols to basically trying regularizations or constraints which make the representation stable across a given unit. And then if you have more units, we basically get more precision over time. And today I wanted to show you 3 approaches that we have been trying for it. One of them from a few years back from a JSOLT workshop on how this can be done with autoencoders. Then one where we tried to adapt this to contrastive training techniques and what happened out of it. And one which is still very much work in progress on how you can post-process the extracted features using scalable and fast methods, which try to work in the discrete domain. So let's start with the autoencoders, and this is this paper from JSOLT. So when you take an autoencoder, you basically take your speech and then put it through the encoder, get the sequence of latent vectors, put them through a decoder, and reconstruct the speech. And the quality of the representation here in the middle really depends on the regularization or on the constraints you put into it. So we have denoising autoencoders which inject noise. We have variational autoencoders which say that this is sampled from a Gaussian. We have quantized autoencoders which try to learn a representation which is discrete. And in a sense, what you would want to have directly from my desiderata to have piecewise constant representations, we would want to have an encoder which tries to round up the representations such that there are blocks with similar values. So basically go from those slightly different colors to this nice picture with blocks of same colors. And this is implemented by imposing a special optimization objective or special constraint on the representation, where we would want to round all the representations such that the rounding error is small, so it's a lossy form of compression, and there are only a few changes of the coding vector. This also works and was originally developed for discrete autoencoders, and this gave us this little side objective to optimize during training. So we would essentially be quantizing or rounding up each of the input vectors to a quantized vector such that there are not too many changes of the quantization code. And this is a tiny dynamic program that you have to solve within your training loop. You can do it greedily, and this doesn't slow down the process that much. And this basically stabilizes training, and we got improved results on using those techniques for learning representations on handwritten text. So basically, the error rate went down, the accuracy improved, and so on. So this is a very nice proof of concept which worked. But then the world moved ahead, let's say, and the contrastive learning techniques started to win in the representation learning war. And we were trying to adapt this segmental approach to it. And in the end, we came up with some loss function, which also promotes piecewise constant representations that I will try to show you right now. So a direct port of this segmenting piecewise constant bottleneck didn't work, but something similar did. So let's start with the CPC, the excellent feature learner, which influenced also the wave to vacant and similar ones. We take this speech, we are extracting a latent representation at a fixed rate, which stems from the sampling rate. So this is very much a frame synchronous approach. And then we are making predictions of the frames to come, and we train the system using a contrastive loss, right? So for the step ZT, we are making predictions of up to a few frames, in this example, up to 6 frames into the future. And then we extend this latent representation by one element, and then we make another set of predictions, another one, and this learns really good representations. So what we thought is, what would happen if we somehow made fewer predictions than the frames we are trying to explain? Or in other words, what would happen if we wanted to predict the next few blocks of basically equal or identical representations, rather than to predict at this fine grain rate what happens in every next frame? And this gave us the aligned contrastive predictive coding, where basically we make few predictions in this example 3, and we align them to the upcoming set of frames in this example 6. And then what you can notice is that if several frames, or the representation in several frames, gets aligned to the same prediction, they are pulled together, so they are trained to be the same. And this basically is how I see that this relates to this piecewise constant representation. We force the system to somehow cluster the upcoming frames into a few groups, and those groups are trained to be together. The other way to look at it is that we are trying to make the model predict what will happen, but not exactly when. So we are solving a slightly easier training task, which may also be beneficial. We don't have the model to make predictions at the sampling rate. We have to make the model make predictions at the content rate. What happens next, not exactly when does it happen. And this actually improved the representation pretty dramatically when we analyzed it. First, a few visual results. So on the left, there is the self-similarity between representation frames for CPC. On the right, there is the self-similarity between neighboring representations for ACPC. We do see those weird bands on the left. I believe that it's CPC somehow cheating and encoding the relative position of frames between themselves. So it's somehow able to use the convolutions to mark the frame index modulo 6, I guess, in this plot. And then this helps it to distinguish between essentially different frames. But this is a totally spurious signal, right? When the model cannot really make predictions at this rate, it's better. And then on the right, we start to see those blocks of self-similar frames. And hopefully you see it on your screens. There are those thin white lines. These are the ground truth phoneme boundaries. So we start to get a representation which is has this block diagonal similarity structure, and the the boundaries between the blocks tend to coincide with phoneme boundaries. So for us, this was a sign that this improves the piecewise content or segmentability of the representation. And qualitatively, we see that neighboring frames are more similar, especially there is this little bump. So in ACPC, this aligned CPC, they are neighboring frames which are more similar than between random ones, and this basically shows that we do better on keeping tiny changes for frames in the same phoneme and then abrupt changes at phoneme boundaries. And this also improved the clusterability of the representation. So here we basically see what is the mean square distance for k-means clustering and what's the normalized mutual information between the clusters when the number of centroids grows. And here ACPC has a lower approximation error, a higher mutual information. The vectors have normalized length, so this roughly translates to how the clusters are pure or coherent. And this also yielded better performance on downstream tasks. So essentially on the CPC for zero speech, we were able to go down by a percentage point by applying the aligned contrastive predicting cost. It also turns out that the exact number of frames you are predicting doesn't matter as long as it's smaller than, as long as you are making fewer predictions than the number of frames that you align to. So this was fairly stable with respect to hyperparameters. And having done that, we basically tried to go even more into this direction and try to have a model which would have two layers. So it would have this first CPC layer or ACPC layer, which would learn this blockwise, similarity, then somehow cluster it, and then run another self-supervised head, which would learn the representation, really making a step at transition at every detected phoneme change. And here we have the results of it, and we discovered that there is really a trade-off. If a model is better at the downstream task we care about, such as phoneme prediction, it's worse at segmenting. If the model is better at segmenting, it's worse at prediction. So we are comparing here essentially the Crook model, which is a segmentation model, which is and CPC, these are both models made for segmentation. They win on the precision recall, every segmentation metric you can have. But then when you are looking at the actual predictive accuracy of the representation, ACPC wins. So it's bad, right? We would want to have a representation which corresponds to phonemes, but when you actually try to use it, it's either you get the boundaries right or the contents right. So we tried to reconcile the two approaches, and this is this year's ICASP. So we basically found that there is a difference between how you use the context network and how many steps ahead you predict, and that this drives the model to be either better at recognizing boundaries or at keeping contents, and hence the multi-level ACPC architecture was born, which tries to have the ACPC head to be good at predicting phonemes, but then also have a boundary detector and then have a second head which runs at a content synchronous level, not at a frame synchronous level. And this sort of gives you the best of both worlds. It's not the best in both contexts, but it's decent in both of them. So it gives competitive segmentation performance, and it gives you a good phoneme recognition performance. So I guess this would be the direction where things should be going, even though there is a little bit to fix. And then finally, an approach that we also invested some time, even though it's still very preliminary. We are actually looking for ideas on how to improve it, and it was basically feature post-processing. So the intuition was we take our audio, we run it through CPC or some other feature recognizer, and then we can do k-means, and these are already pretty good at detecting phonemes. But what if we tried to somehow work in the discrete domain with those cluster IDs to try to find frequently reoccurring patterns and somehow learn to segment this representation. So you can try to apply some heuristics, which would do something like random encoding, right? Basically collapse runs of the same cluster. And this helps you some. This is not a super good segmentation model, but this goes slightly along that way. Then you can also try to do sentence piece or models which discover tokenizations on this discrete representation. And this basically allows you to say that you have those frequently reoccurring patterns of cluster IDs that you could call pseudophones, and tune this sentence piece to extract sequences of frames which are roughly the correct length for a phoneme. And I guess this is very similar to the models Herman was talking about. The only change here is that we apply models which work in discrete domain as opposed to the continuous domain. You can use many algorithmic tricks to make this really, really fast. Like sentence piece is able to learn a tokenization of gigabytes of text in a few hours because it's working in the discrete domain, which would open the possibility to essentially do this term discovery or pseudophone discovery on large corpuses of speech. And so far we know that if you do this, and then you're trying to recluster, so you are trying not to greedily assign every frame to the nearest cluster, but you are trying to somehow combine the distance from the continuous representation to the clusters and the probability of the sentence pieces. You get something which is slightly better in terms of mapping to phonemes. So you can then basically this cleans like pointwise errors and so on. So there is something in this approach, but the improvements we see right now are not very how to say significant. So we are trying to improve this, and I guess there is a lot to be done here, because for me this pre-training of discrete representations and then working in the discrete domain allows one to process large scale data, because there are many tricks to algorithmically discover reoccurring patterns in discrete data. So in summary, I guess that promoting those piecewise constant representations really helps, but then it's sort of tricky to really make use of it in the model. The models which still run at the original sampling rate of the data, or so at the sampling rate, they are still pretty strong, and it's challenging to have a model which would reduce the time resolution in a smart way and offer competitive performance. But we want to get there. Finally, 2 slides, because I've changed my affiliation from the university to a startup. So we want to do the same thing, but for GPS traces. We want to discover, structure them, go from unordered maps to essentially nice little diagrams of processes, and we do it by techniques really similar. So we try to segment the traces by doing EM and techniques from NLP and so on. So just a little plug in the speech processing workshop. If you would want to apply similar techniques in logistics domain, please reach out to me. Thank you very much. The links to papers are here. The links to the code are here. If you are interested in this logistics, please reach out to me. And then a very personal thing at the very end. I'm sorry for another personal thing. It felt really weird for me to prepare for this talk, because while I was searching for slides, I've noticed that exactly a year ago, at the same time, I was giving a talk for a data science school in Kiev. So it felt weird that last year they were learning about speech processing, and this year they are learning, I don't know, how to make Molotov cocktails. So I guess we can all help them by showing their support, and I guess that the support should be extended really to the people in Russia and Belarus who also want to get rid of their dictators. In Belarus, they are trying to do so for over a year. And I guess that the historical winds are blowing strong right now. My country was really lucky to be able to do it. And it's part of EU, NATO, and I am safe at my home, but they really need our support right now to be able to enjoy the same kind of freedoms. So sorry for this, and thank you for the invitation. Thank you for listening.
Thank you very much, Yang, for the insightful talk.